Hi, folks. Welcome to the second part of our session tonight. We have with us Jim Andrews, KH6HTV, who will talk to you about fast scan television. Um, this fast scan television's been around for quite a while, but it's really going into a new stage with digital fast scan TV beginning to take over as it has in the commercial world as well. And we're really privileged to have Jim, who probably knows more about this subject than most anybody. And it's a really interesting one, and I'm fascinated. And it's always a new presentation, so if you heard it before, you're going to enjoy this one also. So, Jim, it's all yours. Thank you for helping us out with this.
Okay, so what do I do? How do you get me to be
You
on
can
screen?
You're on. Start talking.
just do your share. If you share,
Oh,
you'll be all right.
okay. All right. So I'm Jim Andrews, KH6HTV, and I live in Boulder, Colorado. The KH6 call is a reflection that I used to be a snowbird for many years in Hawaii. Um, but that's a totally other story. So I've been involved with amateur television and the fast scan aspect of amateur television really since the mid 1970s. And we have had a television repeater here in Boulder, Colorado since the late 70s. And it has gone through quite a few iterations and now is a fully digital repeater. But anyway, I'm going to bring up a set of PowerPoint slides at this point. All right, so am I sharing yet? No, not yet. Okay, I want to share the screen. Okay, do we have that on full screen at this point?
Yeah, I see your PowerPoint. It's not full screen. I still see some of your desktop. That's good. There we go.
Okay.
Perfect.
That's good.
Okay, so I do have a website here that's simplymycall.com, and you will find an awful lot of information about amateur television at that point. And my email, if anybody wants to contact me, is also my call sign at gmail.com. I'm a little bit older than this photo here that was taken a few years back, but okay, so amateur television. So let's first immediately distinguish this from slow scan TV. So when you talk about television for the hams, most people think immediately slow scan. This is not that. On slow scan, we do that on the HF bands in a narrow single sideband channel of only 2.4 kilohertz. And we send one single image, one frame per minute. Fast scan TV. Okay, the FCC has allowed us for many years to do broadcast quality live television. And hams tend to call that fast scan to distinguish it from slow scan, or ATV, or amateur television for short. Now we're talking 6 megahertz wide bandwidth channels, and we're going to send 30 frames of video per second. So what are the standard TV channels? Here in the United States, they are 6 megahertz wide. In some other countries around the world, they are 7 or 8 megahertz wide. They're broken into the UHF or VHF low bands down around 6 meters, the VHF high band, which essentially we're talking the 2 meter region, and the VHF or UHF band, which is essentially our 70 centimeter region. Sorry, ignore that cell phone. Cable TV, though, covers all frequencies from essentially 2 meters all the way out to 1 gigahertz. So the 70 centimeter band is the lowest ham band we're going to be using for amateur TV. Well, let's look a little closer at that band. We have 30 megahertz at 70 centimeters, and so divide 6 into that. That says we could potentially have up to 5 TV channels in the 70 centimeter band. And it turns out, I noted channels 57 through 61, those are in fact cable TV channels. So the fact then was a TV receiver on cable TV would actually work in the 70 centimeter band. Of that, the ARL band plan, if you'll notice, channel 57, 58, and 60 are designated for ATV. Channel 58 there is designated as a simplex channel, and repeaters would have an input on channel 60 and an output at the bottom end of the band on 57. TV has been around a long time, almost 100 years. It initially developed actually in the mid-1920s, with literally the first broadcast by the BBC in 1929 and the National Broadcasting System in 1939 in the US. They used the technology that was available then. In other words, amplitude modulation, AM. And by 1941, the FCC literally etched into stone the TV standards for TV, and they were based upon the technology that was available at that point. Those standards remained changed for 60 years. They only updated them slightly in 1953 when they added color capability. So let's now talk about some of the TV basics. We go back to having cathode ray tubes, basically for the image pickup and display in the earlier televisions. And an analog television signal is you're going to scan an electron beam across the face of that cathode ray tube. And so we're going to start with an electron beam in the upper left corner, and we're going to scan it from left to right. And then at that point, we're going to create a pulse in the signal that's a reset pulse, horizontal, and we call it the horizontal sync pulse. And it's going to tell the TV receiver, hey, jump the electron beam back over to the left side and index it down a notch, and now scan again. And so you're kind of scanning from left to right and then from top to bottom. And the older systems actually then interlaced scan lines. So that's what we're talking about there. Total of 525 lines, but only, okay, now once the electron beam reached the bottom of the screen in the lower right corner, everything had to be reset back up to the top upper left corner. So there was then a pulse, a much longer duration pulse that was called the vertical sync pulse that caused this system to reset. So because of the presence of the time that's occupied by these pulses, not all of those 525 lines were displayed, only 480. So the end result is we ended up with 640 by 480 distinct individual pixels. Let's look at what the video signal looks like coming out of a TV camera. So this here would be an oscilloscope trace, voltage vertical and time running horizontal. The standard video signal was defined to be 1 volt peak to peak into a 75 ohm termination. And they use 75 ohm coax to route video signals around the studio. So you can see here, this is one horizontal line of video, with a synchronizing pulse to start it. And then we define the top level of that signal to be white, and then right behind the pulse, sync pulse, is the black level, and anything in between is gray levels. Okay, now when we added color, that was actually a very clever scheme that they came up with, and they ended up putting in a meshed into the frequency spectrum of the video signal an additional signal that was interleaved with it, and we'll talk about that on the next slide. But this would be a color pattern then that might be shown here on the video signal. Okay, so let's also talk about modulation methods. As I indicated before, the dominant system for analog TV for up until almost year 2000, AM TV. And then they also modified that a bit by what was called vestigial upper sideband TV. And this basically was a modification of AM by filtering off a portion of the lower sideband. We'll show that in another slide here, how we do that. FM was also used, but that was primarily used for the studio transmitter links and so forth, electronic news gathering. And then once we get to digital TV, in modern day, there are several variations. Okay, here now is the spectrum of a 6 megahertz wide transmitted signal with analog television. So we put the video carrier for the AM signal at 1.25 megahertz below above the channel lower band edge. The video, black and white, a really pure black and white signal, occupied about 4.2 megahertz of bandwidth. So that is what we're showing there in the gray area called luminous. And then for vestigial sideband, so we know when we have AM, we generate both upper and lower sidebands equally. Well, the engineers discovered that they could chop off part of that lower sideband and still the system would work quite well. So what we're seeing there is we filter off beyond 1.25 megahertz any of the lower sideband. Okay, now we're also showing there in red, this is where in the 1950s, when they decided to add color, they put the color in there with a color carrier at 3.58 megahertz with independent upper and lower sidebands on that to carry the color information. Okay, we now also want to have audio. So what they did was add a second transmitter at this TV station running FM audio, and that transmitter was located 4.5 megahertz above the video carrier. So this is what the total spectrum looks like on the old analog system. Okay, so now we get to hams sending out one of these signals with a total AM. This would be what the signal would look like from if you were a ham running 70 centimeter AM TV up until recently. This is probably what your transmitter was putting out. This spectrum analyzer plot here is 10 dB per division vertical and 10 megahertz per division horizontal. So you can see that chews up a lot of spectrum. Okay, so if you were a really spectrum conscious ham at that point, you would have instead tried to run vestigial upper sideband. So this would be what an amateur vestigial sideband signal would have looked like. Much cleaner. Things have been cleaned up a lot and did not chew up a lot of spectrum. Okay, let's now also compare different modulation schemes. Here are horizontal, we're spanning 50 megahertz, so the horizontal scale factor here is 5 megahertz per division. And we're showing the relative spectrum occupied by, on the left, that would be a commercial broadcast vestigial upper sideband TV signal. The very strong peak is the video carrier. The next strongest peak to the right of that, on this is displayed in yellow, is the sound subcarrier. And then a little bit below that, you can see the color subcarrier at 3.58. In the middle, we're talking an FM signal carrying that same 4.2 megahertz bandwidth analog video signal. Now we're running 4 megahertz deviation on that particular plot. And you can see how much spectrum is chewed up there. On the right, we're now looking at a modern day digital television signal. And in this case, it's still occupying 6 megahertz bandwidth, but it looks just like white noise raised on a rectangular pedestal. Okay, so what were the limitations in analog? Well, the biggest one was the fact that it used AM modulation. As we hams know, we pretty much don't use AM anymore in favor of single sideband or FM. So with that 4.2 megahertz bandwidth, that meant the AM bandwidth required was greater than 9, but they used vestigial sideband to cut it down to 6. Those standards were set 1941, the year I was born. Okay, what limitations? Well, the big limitation is snow in the signal with weak signals. To get a perfect AM TV signal, you need 40 dB of signal to noise ratio, which ends up being equivalent to having a minus 60 dBm signal at your receiver for a perfect picture. The other defect that was often seen was a ghost or a multiple images in your picture, and those were a result of multipath, multiple paths for signals to arrive at your TV antenna. FM was added later for microwave lengths, and it works much better, as we well know, with weaker signals, but consumes more spectrum. Thus, we can't use that at 70 centimeters. Okay, so when we give signal reports on the air, unfortunately, everybody gets a 5.9 these days, no matter how poor the signal was. But in reality, when we looked at audio reporting, the first digit was 1 to 5, which was a readability. If you gave somebody a readability of 5, that meant you had perfect armchair copy. A 0 or 1, man, I can barely understand what you're doing. And then the second digit was the S meter reading. Okay, so for ATV hams, we gave a rating on what the quality of the picture was we're seeing in the analog days. So these are examples of those. So P0, you can just barely tell that there was sync there. P1, you could see some big characters, and that was about it. And a P5 is a perfect picture. All right, let's plot received signal strength at the antenna input of our TV receiver versus these picture ratings. And so we can see here on the vestigial sideband, we have a linear curve starting down around minus 100 dBm with just something barely detectable. And it turns out for a 6 dB improvement in receive power, we come up 1 P unit. That's the same definition that we used for S units on our S meter, was a 6 dB change. And we can see we have to get all the way up to about minus 60 before we get to P5. We look at the FM plot, we see the enhancement there in we can get to a P5 picture much sooner with FM. Now with digital, there's no intermediate P1, P2, P3, P4. With digital, we either have P0, absolutely nothing, or we have P5. And so the digital here, we have what we call the cliff effect. And it turns out that cliff is about 1 dB wide. And so if on your digital home TV, you start to see a little bit of breakup, pixelization on the received picture, literally, if you lose about another 1 or 2 dB of signal strength, your picture on that digital TV has totally disappeared. It's gone. Okay, let's pause right here and see if there are any chat questions appeared.
None so far. Anybody have any questions?
Okay, let's move on.
Move on, Jim. Thanks.
Okay, what do we use for video sources? Well, for ham stations, we tend to use the camcorders. Those are great because they got the built-in zoom, little monitor screen, everything else we need. Your home PC computer, the newer ones built more recently, all have an HDMI output to drive an external monitor. Well, that means it's perfect. We can plug that right into our amateur TV transmitter or something like a DVD player. Okay, so what do we had in AM? Well, in those days in the 1970s or the earlier days with TV sets, you could receive, you just put the TV in cable mode and tuned to any channels 57 through 60, and lo and behold, your home TV was in fact your receiver for the old analog TV. And what did you use for a transmitter? Well, to be perfectly honest, there was one dominant supplier for many, many years in the analog days for amateur television, and that was Tom O'Hara out of Los Angeles and his company called PC Electronics. So pretty much anybody that was doing amateur television in the analog days, they were using equipment that was built by Tom. And so this would have been his classic transmitter for 70 centimeters, put out 20 watts. Basically, it was really a transceiver. It also included a tunable down converter to take a signal and bring it out on channel 3. So you may still find these things kicking around at Swap Fest or on eBay. But yeah, so PC Electronics was the dominant supplier. Okay, unfortunately today, okay, so when the FCC decided we were going to go to digital, they did put in a 20-year crossover from the time they said we're going to go from digital analog to digital, and they mandated that all television sets sold in the United States must include an analog TV tuner. Well, that requirement expired in 2017. So the likelihood of you buying a TV set now at Best Buy or Walmart and having an analog tuner in it now, it's probably not going to happen. So if you still want to do the old analog, what was called NTSC analog, fortunately, China does sell us some set box tuners, and I've found one recently that I took a picture of here and evaluated, and it does work well for $65 on Amazon. So those are still available, but that's what you would have to get. It'd be very similar to the little set-top box you use for cable or satellite. Okay, so how were the older TV transmitters built? Okay, as I mentioned earlier, the broadcast people actually used two separate transmitters, one for the video and one for the audio. Well, we didn't really need to do that, so hams mixed the two and just made one single transmitter. And this would be the basic configuration of any of those transmitters that Tom O'Hara and PC Electronics made and sold. Tom has told me he sold thousands of those things over about a 40-year period of time. Basically started out with a 100 megahertz crystal oscillator, multiplied it 4 times up to the 70 centimeter 400 megahertz band. And then we're going to have a video input with a video amplifier, and we're also going to have an audio input that we're going to go to a varactor diode, and we're going to have a sound subcarrier oscillator running at 4.5 megahertz that we're going to FM with the audio. Then we're going to use an integrated circuit operational amplifier, summing. We're going to add those two signals together. And we're going to drive a transistor that's attached to the collector of the final RF amplifier in our transmitter. And so we're going to AM modulate. So we're going to pump the collector voltage on the final amplifier to create AM modulation. So that's basically what was done in all of those transmitters. And how did we then convert it to a vestigial upper sideband? Well, it's turned out to be a pretty expensive way to do it, but it's a piece of machined artwork. This is an interdigital bandpass filter, and each one of those copper rods is a quarter wavelength at 70 centimeters, and then they are tuned by a small screw that's off the open circuit end of the rod. And so that's the and those even in the 1980s or whatever cost several $100s. So it was not an inexpensive way to get vestigial sideband, but it gave you a perfect 6 megahertz wide bandpass filter that would chop off the part of the lower sideband. And those were mandatory when you built a TV repeater. Okay, now there is another option, and the cable TV network had what they called their modulators, that they would rack up maybe 100 of these things side by side and generate a perfect vestigial sideband signal on every adjacent channel in the cable system. And so this actually turned out to be a very attractive way to make vestigial sideband for analog. Was to take one of those cable TV modulators, which would put out at most maybe a milliwatt of power, and then just follow it with linear RF power amplifiers. Okay, so here on the left is an example of a cable TV modulator. And to be perfectly honest, most of those have been obsolete. They were made by quite a few different companies like the Drake Company, Blonder Tom, Maycom. I have found that the Toner Company still does sell this particular modulator, and I have bought one recently, and it does still work great. So you can still buy that modulator. It costs about $170. The other alternative is the Chinese offer some lower cost modulators that are fully synthesized. This one here is about $80. And I've also found one since I made up this slide for about $40, and they both work quite well, but they do put out AM. They're not vestigial sideband. So bottom line is if you want to get on the old AM or vestigial sideband TV today, and there are still some TV repeaters around that are running that. So if you're wanting to get into those groups, you have to do it. The way to do it is buy one of these modulators and use this scheme with a linear amplifier afterwards. Okay, so here's some typical amplifiers, and I'm immediately going to make a disclosure down at the bottom. I'm not an unbiased showing these because I am a supplier of RF linear power amplifiers, and I've sold a lot of these things to hams, and they're also being used in TV repeaters. But the amplifier there on the left is capable of putting out 25 watts of AM. One on the right is 10 watts. And why two different ones? Well, how much current they're going to pull. So our ARS group here in Boulder uses these on the right because they don't pull as much current if you're going out in the field and have to run off of a battery that you're carrying on your back. FM TV. Well, as I showed earlier with the spectrum, that's a much wider one. So we're only going to use that on the 23 centimeter or higher microwave bands. 23 centimeters, we got 60 megahertz of bandwidth. But FM is going the same way as AM. It's become obsolete. And if you want to find FM TV equipment, the only stuff you can find today is really for the 5.8 gigahertz band. And it's was intended for putting a video capability on hobbyist drones, what they called FPV, or first person view was the acronym used. Very inexpensive though, and extremely good quality. So what I'm showing here, I actually paid $30 for that pair of a transmitter and a receiver, fully synthesized with 40 channels in the 5.8 gig band. And it really does work extremely well. So if you want to try amateur television today on a low budget, go for the 5.8 gig band and buy some of this FM gear. It does work really well. Okay, let's pause here again, see if there's any questions.
Not so far. Oh, wait a minute. I'm going to hold this one, so go ahead for now, Jim, and we'll bring it up in a little while.
Okay, moving on. All right, let's now go to digital television. Okay, so I claim that ATV is no longer amateur once we've gone to digital. You're going to have perfect pictures, high definition. We're running 1080p high definition, and we end up with CD quality stereo sound. So this happened to be an assortment of pictures of some of the hams that show up every week for our TV net here in Boulder. And they're all running high definition digital. And it's all being funneled through our local TV repeater. Okay. Now, at this point, I am going to make a distinction of what I'm going to call DTV or digital television versus mesh networking. And I think there was a question like that in the previous presentation about ARCNEM. So I'm going to say mesh is a point-to-point, whereas digital television can really be considered wide area broadcast one way. And mesh requires transmit receive capability at both ends of the circuit. Digital television, one transmitter, unlimited number of receivers. We're talking the equivalent of broadcast television. So mesh requires handshaking for data transfer. DTV is broadcast. There's no handshaking required to receive. So I'm not going to cover anything about mesh in this talk. Okay, what are the broadcast standards that are used for digital television? Well, here in the United States, it's one that's called 8VSB, or also ATSC, and the ATSC stood for Advanced Television Subcommittee. And that's the standard that's currently used in the broadcast TV industry here. And you'll now also hear it called ATSC 1.0, because they're now also offering an enhanced version that's called ATSC 3.0, which is not backwardly compatible to 1.0. Okay, the others are ones that are used essentially elsewhere in the world. DVB-C stood for cable. DVB-S stood for satellite. And DVB-T was for terrestrial. And each one of these is different in terms of how all the data is encoded because of the nature of the medium under which it's transmitted. For cable, you have a perfect environment where you can have strong signals and low VSWR, which means no multipath. It's the perfect transmission environment. So it requires the least amount of extra encoding and error correction. DVB-S from satellite is optimized for very weak signals being received from satellites. But in that case, the signal is coming from outer space. There's no multipath to be dealt with on the S. DVB-T is the worst environment, and this is the over the surface of the Earth terrestrial path where you can have very strong or very weak signals, and you can also have the presence of multipath reflections off of buildings, mountains, Doppler shift from moving vehicles, you name it. And so the DVB-T requires the most aggressive types of encoding to be able to get a good signal through. It does turn out that the majority of the hams in Europe are using DVB-S, and most of the hams in the United States are using DVB-T, and very few are using the American standard. Okay, yeah, that's basically what I was going to say in this slide. Yeah, there is a couple of groups. I think there is a group in the San Francisco Bay Area that is using DVB-S, and a group in New Orleans that's using the ATSC system, and also a group in San Diego are using ATSC. But everybody else is going to DVB-T. So the US standard is only used in the US, Canada, and Mexico. Okay. The DVB-T uses what is called co-FDM, and it actually consists of either 2,000 or 8,000 subcarriers in that 6 megahertz wide channel. And then, so basically the idea there is you might lose a few, might have some interference that knocks out a few of those subcarriers, but the vast majority of them are going to get through, and it all uses packetized digital data. The modulation schemes are either QPSK, quadrature phase shift keying, or 16-level QAM, or quadrature amplitude modulation, or 64 QAM. It does include dynamic channel characterization and correction and forward error correction. So it actually sends pilot carriers mixed into the 8,000 subcarriers, and it characterizes the dynamics of the channel. So you could have multipath, but you could also have Doppler shift on multipath. And the receiver then is able to compensate for this and eliminate that. So you have zero ghosting in a digital signal. So it becomes extremely tolerant of extreme multipath and does work quite well. It eliminates Doppler shift too. Okay, now with these three modulation schemes, there is a trade-off in the receiver sensitivity. So these numbers here will show you a typical receiver. This would be where that digital threshold occurs, whether you either get a picture or no picture. So with QPSK, it's going to be the most sensitive. And if you add a preamp, you can maybe get another 3 dB, or if you go to very aggressive forward error correction, maybe another 3 dB. Okay, so why would we want these differences between QPSK and QAM? It's really how much data rate you can pump through that 6 megahertz channel. QPSK, we're looking at about 7 megabits. 16 QAM, we're up to about 15. And 64, we're up to 22 megabits. Well, why would we want more data rate? Well, it's really, if you've got a really fast moving video of trying to follow sports, the higher rate QAM with higher data rates will follow it better. But for typical ham installations, we're running low power marginal antennas. That 15 dB difference can often mean the difference between picture or no picture. So pretty much all our ham activity, we use the most sensitive QPSK lower data rates. Okay, what do the equipment look like? So we're going to start off with a video source, typically our camcorder, and these things all have an HDMI audio video output. We're going to go to a box we call a modulator. We plug the HDMI input. And the modulator has got a pretty powerful computer in it that's going to massage all this video data and put it into the right DVB DHT format, and it's going to include a frequency synthesizer to put us on the right TV channel. But the output of that modulator, again, is going to be weak, down to the order of a milliwatt. So we need to have a power amplifier to boost it. But I need to emphasize the word linear. This is a pretty complex waveform. It looks like white noise with a lot of peaks and valleys in it. You don't want to chop off the peaks. You don't want to destroy it, or the bit error rate goes to hell. So you must emphasize linear. You do not use a Class C FM amplifier for this. Receiver, okay, same thing. It's going to have the signal coming in. It's got a powerful computer in it that's going to decode all this stuff, and then eventually going to pump out an HDMI audio video signal that you run to your modern flat screen color monitor. Okay, all right, well, here's a typical amateur television total transmitter. We start with a camcorder on the right. In the middle, there's a very small module. It's the modulator. And then in this case, we have the power amplifier. This is the same amplifier I showed you earlier that ran 10 watts for AM television. We're going to get 3 watts out of that same amplifier for digital. And we're looking at it rough to get you into TV here. You're looking at roughly the amount of bucks that you would go spend for an ICOM 7300 entry-level HF rig. Okay, where do we get the equipment? Well, this is the ICOM, if you will, for amateur digital television. So instead of going to ICOM or Kenwood or Yaesu, we go to a company called High Des in Taiwan. They have reasonable prices. As you can see, I said the modulator was $400. They definitely support the amateur TV market, and I say they're unique in providing lower bandwidths. So I earlier mentioned that the channels were 6 megahertz. That's the standard in the US. TV channels in other countries might be 6, 7, or 8 megahertz. Actually, in response to requests from amateur TV hams, High Des engineered their equipment. They will go down as low as 1 megahertz bandwidth and still give you really great digital TV. They sell via website on eBay, and we get very prompt shipping, typically within about a week to 10 days from them. So this is what their modulator looks like. That sells for $400, and it covers everything from 100 megahertz all the way to 2.5 gigahertz. So that covers 4 ham bands for us. And again, programmable bandwidths anywhere from 1 to 8 megahertz. They also sell a companion receiver. This looks in the same box. This one is only going to cover the 70 and 33 centimeter bands, and its bandwidth is capable of 2 to 8. $120 for this. And you program this using the remote control. There's also even less expensive receivers that you can buy. These would be the equivalent of set-top boxes like you get from the cable company or satellite people. And you find a lot of these on the internet at Amazon and eBay. And quite inexpensive, typically under 50 bucks. They only work on 6, 7, or 8 megahertz. And I do have a caution that some of them don't cover the amateur band, but a lot of us are using these also. And here's the least expensive, a USB TV tuner dongle that you can buy to plug into your PC computer. And you can get these down around, a lot of hams have used these things for inexpensive SDR radios. Unfortunately, you have to put a different driver in your computer to make it work for as a TV receiver. And it's been kind of a pain in the neck at times to try to sometimes get them to work. Okay, well, I must warn you, there still will be some setup required for digital TV, and definitely not as simple as the old analog. But I claim it's far simpler than DMR and D-Star, and also much simpler than even programming many FM handhelds. No registration required, no PhD required, but still some setup is required. I do offer an application note on my website to help you do that. Okay, let's stop here again, see if there's any questions come up yet.
Jim, I don't know if this is the appropriate time, but could you walk us through what a typical TV QSO is like? Is it, you talked about
Okay, sure.
the repeaters and, just some examples given your situation there.
All right. Well, to be perfectly honest, maybe you might say the TV community is the lunatic fringe of the amateur community. There's not a
Wow,
whole
the
lot, there's
fringe
not a
of the
whole,
fringe, right?
yeah. Well, amateur radio is full of fringes. Uh, there's not a whole lot of people involved in TV, and it's definitely not something that you would typically just get on the air and call CQ. Although there is a group back in the Midwest, well, you call it the Midwest, it's really the Ohio, Kentucky area. I grew up in Kansas. I thought that was more the Middle West, but in any event, there is a group of hams that are involved in wanting to do long distance communications, particularly back in the eastern part of the U.S., where you much more often have troposcatter. Well, like the previous talk was making long distance contacts. So there is a group that gets together, I think, every morning. Uh, and I think they used to do it on 80 meters, but now they just have a Zoom meeting every morning, and people throughout the area of Kentucky, Ohio, Michigan try to exchange both analog and digital TV signals, but they coordinate it with a Zoom meeting that they all get together. And that's the only one that I'm really aware of that people are involved in trying to make long distance contacts, and sometimes they make contacts over 400-500 mile distance. Some of the hams in Europe, well, they tend to offer more TV contests, and they have made contacts, I think, all the way between Belgium and Greece, for example, with digital TV on the 70 centimeter and also some on 23 centimeter bands. But those usually have to be kind of scheduled activities. People in Japan have had some really long distance over the water between different islands contacts. But the typical usage really revolves around an organized net. And the like here in Boulder, we have a net that we meet every Thursday afternoon, and it runs from about 3 to an hour and a half. But the other thing I will say about TV is the equipment has to be designed for 100% duty cycle. The typical voice communication using your handheld or in single sideband is intermittent back and forth, back and forth, back and forth communications. So your transmitter is not on very long. When we're running TV, the transmitter might be on for 10 minutes. It might be on for 2 hours. It might be on for 24/7. So it's got to be rugged and just be able to take 100% duty cycle. So on our net, we have a two-way conversations, but typically everybody will check in, and net control will then say, "Okay, Jim, it's your turn. Put a TV picture through our repeater." And so I'm going to sit in front of the camera, and I might be on the air for 10 minutes, but I'm doing a two-way conversation. People are hearing my audio coming through with the TV signal, but they're talking back to me on 2 meters. And so it's essentially duplex type conversation. But it's more than just somebody sitting in front of a camera. We might show, we may have taken a vacation and somebody has shot a really great video of their vacation trip, or we're talking about homebrew projects. So we actually get the camera over to the workbench and start showing what it is we worked with. Or we can also patch the HDMI from our PC computer and maybe pass over some schematic diagrams or share other pictures. So that's kind of the nature of what TV conversations and so forth are like.
And you're doing that through a repeater.
Well, in our case, a repeater makes it work so much better for everybody because they have. I mean, why do we use repeaters on 2 meters
Exactly.
for voice? It makes it so much easier to have a wide area of contacts. So
yeah, I think you showed a picture. You showed a slide earlier with 4 or 5 hams.
Exactly. Yeah, they were all participants in that net.
That's kind of your net, and that's once a week or daily or when you feel like
it's once a week.
Uh-huh.
Yeah. And one of my tail end slides here, I'll get into the one other application on it, but maybe I'll hold that off till then.
One other quick question. Excuse me. You had something about, I guess you used the word broadcast versus mesh. And I mean, that's not, it's kind of inconsistent when people think of broadcast and they worry about the legalities of that. But when you say broadcast, you're just sending the same picture to the whole net, for example.
Yeah, well, I'm sending the picture out. I mean, it's just like when any of us get on 2 meters or HF, we blow our radio signal out to the universe. We don't control who can receive our signal.
Got it.
That's to me, that is broadcast. We're casting it out, and anybody that has the appropriate receiver can receive it. And I have certainly been contacted by people that say, "Hey, I saw your picture," type thing. So yeah. Okay, shall we move on?
Sure, go ahead.
Okay, so let's talk about how we're going to rate RF power. for different modes. Okay, so if we're running FM, we're running that power amplifier absolutely as hard as we can. We're saturating the output of that power amplifier. So that's the absolute max power we could get out of that amplifier. We're running single sideband. We're running a linear signal, and maybe the peak of that sideband signal might go up to the max power output. So if I've got a 100-watt transceiver, if I had put it in the FM mode, I get 100 watts out of it. The peak when I'm running single sideband is 100 watts, but the average power is probably a lot less. AM, you're constantly putting out a signal as opposed to single sideband, but there's modulation on it. So we talk about the average carrier power. So let's go back to that ICOM 7300. It was 100 watts, single sideband. The rating on that for AM is 25 watts. And why? Well, you have to back off the carrier power to accommodate when you've got 100% modulation. So the average carrier power is 1/4 of the peak individual power. Okay, let's go to a television signal. In this case, the peak signal is going to be on the synchronizing pulses that we use, and we're going to measure that. And that is going to be rated just like a single sideband transmitter. Only in this case, we're going to measure the peak power on those pulses. The average power on that kind of signal, though, is going to wander around and vary depending upon the modulation, the video modulation. So if you had a bird watt meter measuring average power on an analog TV signal, and the video program is moving around, you've got a lot of changes in the video scene, you're going to watch that power meter needle move back and forth. Okay, the digital signal, that actually looks like noise, it sounds like noise. If you were to tune in a digital TV signal on a single sideband receiver, you would not, there's nothing you could hear there that you could say, I don't hear anything here, it just sounds like noise. Until you look at the S meter, and the S meter is pegged saying, well, there's a lot of power here. Okay, so that it's a noise-like signal, but it's got a lot of spikes in it, and it's got a lot of dips in it. The only way we can characterize that is by the average heating power in that signal. Okay, so let's move over and look at an amplifier and how these numbers are going to compare. So let's take this one single linear amplifier. This happens to be the highest power one that I build. If I run that amplifier totally saturated with an FM or a CW signal, I get 65 watts out of it. If I measure the point at which I get 1 dB gain compression, I get 50 watts. So if I'm running single sideband and I'm willing to accept a little bit of distortion on the peaks, I might run that one up to 50 watts. If I'm going to run this for AM TV or vestigial upper sideband TV, and I don't want to start clipping the sinks off, I'm going to probably limit that one to 25 watts peak. This same thing now, I'm going to run that digital signal through it. I measure 10 watts average power on that. However, so I said I needed at least 8 dB headroom, 10 watts versus 65 watts. That turns out to be about 8 dB. And what So the peaks in that digital signal are in fact hitting 65 watts. But I don't want to chop those peaks off, so I don't want to push higher. I don't want to push the drive level on that digital amplifier any more than 10 watts, or I'm starting to chop off the peaks and the bit error ratio goes to hell, and the receiver can no longer decode that signal. Okay, so again, full disclosure, I have a small hobby business, my ham shack, building these amplifiers. And here's again the picture of the two. So again, the one on the left now, we're getting 10 watts, one on the right, 3 watts. And this is what the prices range on those. And because I'm going to drive these things with a modulator down around a milliwatt or less of power, we need a lot of gain. So these amplifiers have in excess of 50 dB gain in them. What do we use for antennas? Well, we're going to use the same antennas that hams are using for other purposes, with the sole caveat that the antenna must be broadband. We want an antenna that will cover the entire band because we're using a broad signal and we may want to put our TV signal anywhere in that band. Unfortunately, most antenna manufacturers don't tell you anything hardly about their antenna. They may just say, well, it's good for 70 centimeters. And you go turn out it might only really work for the FM portion, the upper 10 megahertz, or it might only work for a couple of megahertz at 432. So we do have some application notes where we've tested a lot of antennas, and we have some that we definitely recommend for TV service, and others we definitely say don't even think about it. What polarity? Well, and that all depends on what your local group is doing, but our Boulder group, because we use it for ARES, we picked vertical polarization because that was most suitable for our use for backpack, portable, mobile, and repeater operations. How about IDing? FCC says we're supposed to ID every 10 minutes, right? Well, in the analog days, that meant just holding up a QSL card in front of the camera, and bingo, you were done. Well, I say it's even more simple with digital television because it's already done automatically for us. You program into that modulator from HiDes as part of the initial setup your call sign. That call sign is not transmitted every 10 minutes. It's transmitted with every video frame that goes out. There's a header on each video frame that tells the receiver how to decode the packet data that's coming with it, and included in that metadata is the call sign. So on your receiver, you got the information button on the receiver remote control. Push that, and comes up on the screen your call sign. And I will admit that there's some hams arguing, oh, that ain't legal. Well, if you don't feel it's legal, just hold up your QSL card in front of your camera again. Okay, how far is my TV signal going to go? Well, my simple answer is line of sight. You've got hills in the way, it ain't going to get over it. The broadcast people put their stuff on really tall towers and run tens or hundreds of kilowatts of power. We're lucky to get our antenna 30 feet up in the air, and probably we live in a valley, and we're putting out 10 watts of power. So don't expect it to go as far as your 2-meter signal. And why? Well, I say it's the law of physics is going to limit this. how much noise is there at the input of your receiver. And so it turns out this is a noise in the receiver is set by an equation called KTB. K being Boltzmann's constant, T being the absolute temperature, and B being the bandwidth. So, single FM signal with 15 kilohertz of bandwidth, noise level minus 132 dBm. Let's go out to 6 megahertz for TV. We're up to minus 106 dBm. So if we're receiving a signal at minus 100 dBm there with digital, we're doing pretty good there. We're getting down close to that noise level. I got an application note that talks about that. Okay, what's the propagation characteristics for us for the various bands? So 70 centimeters, we can't go any below that. Actually, the people in Europe have been allowed to go down to the 6-meter band, and some of them are actually down on the 10-meter band now, running narrower bandwidth digital TV experiments. But in the US, we're limited. We can't go any below 70. But it's really our best all-round band. We got 30 megahertz there, and just overall, it's the equivalent of the UHF broadcast TV band. I say 33 centimeters. Don't waste your time. Too much RFI from unlicensed stuff. I just see the noise level here on 900 megahertz is about 15, 20 dB higher than outside that band. 23 centimeters is really the second band of choice. Biggest issue we encounter there is if you're living in some of the major metro areas, there are FAA radars in the 23 centimeter band that will cause havoc for you. Again, 13 centimeters, fortunately there is a 10 megahertz kind of quote clear channel at 2.39 to 2.4 that's supposed to be just for hams. So you might be able to put one TV channel there, but don't even think about getting above 2.4 because of Wi-Fi. And once you get to the higher stuff, might as well figure that's point to point where we're really using high gain dishes. But people have gotten really long distances beyond 500 kilometers all the way out well above 10 gigahertz with digital TV. So how do we do that? Well, basically, we need to consider the equipment we're using at 70 centimeters to be our IF frequency. So we're going to use that same stuff at IF, but we're going to add a mixer and a local oscillator to boost or self signal up and back down again. One caveat on the local oscillator to make it work with digital: must have very low phase noise. Otherwise, too much phase noise will destroy the digital signal. TV repeaters. Okay, well, in general, I say it's far simpler to build than an FM repeater, but this is what you're looking at typical cost. Here would be the basic block diagram of what's required for a 70 centimeter repeater. Major difference between TV repeaters and voice repeaters: a voice repeater typically uses one antenna and a duplexer and like 5 megahertz spacing between on 70 centimeters or 600 kilohertz on 2 meters. Because of the very wide bandwidth where you're running, a duplexer is possible, but very difficult to build. And if you buy one, you're going to pay a real arm and a leg for it. So we typically just use two separate antennas and space them so that we have good isolation between the two antennas, and then separate bandpass, 6 megahertz bandpass filters. And the only other thing we noting here is we pick off a signal from the receiver that says when it is receiving a valid signal, and we're going to use that to key the transmitter. Here's an example of a basic television repeater, one that I just recently built for our Boulder County ARES group. And this is all the equipment that would be required for that. Our Boulder repeater is actually much more complicated, and it gets to be much more of an engineering project, but this one has multiple receivers. This one has 3 receivers, one for the 70 centimeter band, one for 1.2 gigahertz, 23 centimeter band, and also 3 centimeter, 10 gigahertz. So we've got 3 inputs to that receiver, and the transmitter has 2 outputs. One on 70 centimeters running digital, and one on the 5.8 gigahertz band running FM. And our particular repeater is located not on the side of a mountain directly behind the city of Boulder, but it's about 800 feet above the city. And this is our coverage area from our repeater, and it extends almost to the town of Cheyenne in Wyoming, and covers out, does not cover much of Denver, but covers out onto the eastern prairie. You want to see what TV looks like? You can pick it up on the internet. If you go to the British Amateur Television Club website, it's just batc.org. They have streaming on there, repeaters from around the world and also from hams. And probably of particular interest, well, anyway, and for example, our TV nets that we run from Boulder, we also stream them over the internet, but it's only available during the time our net is actually active. So anyway, that's where you can get a chance to see on some TV in operation. Now, granted, you go to this website and click on some of them. A lot of them might be just transmitting test patterns without live video, but you'll search around and you'll find some live video. Okay, this is the other application of amateur television, and this turned out to be really the most important part for us in Boulder County, and that's supporting public safety through our amateur radio emergency services. In our case, the Boulder County Sheriff in about 1990 came to our local ARES group and said, I want television, and I will supply you with a radio site, tower, antennas, you name it, but give me television. And so here we're pushing on 37 years now later, and we're still doing that. This is just some pictures here. Main things we've covered, things like forest fires, floods, high windstorms, political demonstrations. For many years, we assisted the University of Colorado Police Department with providing television coverage of the football games. We were not showing what was happening on the football field, but what was happening in the stands. We've had riots by the university of students protesting the crackdown on their consumption of beer. Like what we had 20 years ago, we had three straight nights of rioting and burning and destruction, and so our ARS group got to experience tear gas in putting out those. We've also been supporting the Boulder Sheriff's SWAT team, and when the SWAT team was called out for operations, some BCARES members carrying pagers were part of a special subgroup that actually was out on the scene providing coverage of the incident that was transmitted back to the sheriff's SWAT mobile command post. Picture in the upper right there is the inside the EOC, the Emergency Operations Center, during a particular forest fire, and pictures coming in from BCARES ARS TV cameras are being shown on a big screen monitor in the EOC. The picture in the lower right was in the command post at the University of Colorado football stadium. There we had we're capable of putting up 4 simultaneous TV channels on all 4 available 70-centimeter channels. So this is probably the biggest application, really. When it was asked earlier, what's the TV used for? So the TV net is just that's the social side, but it turned out this is probably the more important part of the TV. And as an example, the Boulder County 2 years ago, in recognition of all this, actually gave the ARS group a grant of $30,000 to improve their video system. And so they're in the process of building more repeaters and to scatter around the county. We're weak on coverage into the mountainous area of the county. We've got prairies at 5,000-foot, mile-high elevation, but on the western part of the county, we go up to mountains up to 14,000 feet in the Continental Divide. So anyway, I hope that kind of helps answer the question of why TV. And it turns out TV is the most requested service for the ARES group in Boulder County, over all the other possible things that hams do with ARES. So that's it. I do have on my website a lot of application notes, and the key one that I would recommend you download from there, my website, is my application note 55. It's covers all the things we've talked about today here and handbook. And it turns out this application was actually also distributed by the ARRL on their website. So with that, any final questions?
Any questions, go ahead and send them to me. I just put your link to your website in the chat as well.
Okay. Okay, well, hope a few people stuck around. It's probably kind of a long session here, but
we have over 120 people, Jim, still tuned in.
Okay.
That's a great presentation. Really appreciate it.
That was wonderful. As always, Jim, thank you so much for doing this.
Okay, so hope I didn't get too verbose there. But
Not at all.
It was great. I enjoyed every second.
Okay.
Thank you much.
Right. Well, let's see. I guess we should be able to somehow back off from sharing here. I guess you can unshare me then, maybe,
We
or
can, yeah, we
yeah,
can do
there we
that.
go. Stop share.
There we go. Okay.
Okay.
All right. Well, I'm not going to do the slow scan thing. I was only going to do that if we had time left over. We have two options. I might do it on the night that we do public service because I don't think they have uh, 3 hours worth of time, or we might do it during that week that we're off for the Dayton Hamvention because I don't think most of the people here are going to be at the
Yeah,
Dayton
that's a good
Hamvention.
idea. We could just play it and chat. Okay.
Yeah, so we'll look at that.
All right.
All right, well that's great. I had a great time tonight. Two great presentations. I'll see. Well, I forgot what we have. Oh, next week we may have a change. I'm still in the process. I just found next week was supposed to be the DX presentation, I believe.
Bernie, yeah, Bernie was going to do DXing and then you were going to do the QSL.
Right. So Bernie can't do this. He's in process of moving to putting a house, furnishing his house in Florida. So he's not in town, and he says he just won't be able to do it. But he will be able to do it at almost any other time but next week. So I think I've asked if anybody else wants to switch. If nobody else wants to switch, I could switch my
Morning.
CW in the no code era to the DXing and do the DXing the night of the TV. In other words, switch the 16th and the 23rd for DXing. So
Okay.
it's very possible that CW will be next week and DXing will be the week following. Stay tuned.
Yeah, let me know as soon as possible so I can publish the information to the mailing list.
Okay, we'll try to make a decision before the weekend's out.
Yeah, or over the weekend so we could have it by Monday.
Yeah, yeah,
That'll work.
yeah.
All
I,
right.
I haven't heard back. I only found out yesterday, and I put out something immediately, and I haven't gotten anything back from anybody else. And I thought, well, I can do it
The
myself.
way things happened today, Zach Eflin had Tommy John surgery like all in one day, right?
Yeah, right. That was quick.
Oh, he's on the IL. Oh, he had Tommy John surgery. Oh,
Yeah, the Orioles. I don't know. They got
things happen in a hurry.
black cloud over their heads.
All right, I'm stopping the recording.
Okie dokie.